so that it had a bunch of concrete beams. It was a 6-story building, and up at the top as an overhang over the building, so I'll just make this the building. So that's a building. But at the top they had some beams that came out almost, well, half as wide as the building. Okay, maybe I'll just make it a little bit, not so far. But this kind of came out like 20 or 30 yards. And so underneath this, you could have all the people sitting outdoors in the good weather in the winter in Miami at their little tables, and they could be having their Chardonnay and, you know, and eating their hors d'oeuvres and stuff. And this was going to be a hanging garden because, you know, it doesn't freeze in Miami. And this idiot, this architect, okay, decided to take these beams. Well, if I drew it in 3 dimensions, I can't draw it in 3 dimensions. I'm not drawing it well in 3 dimensions. But, so here's a beam coming across here. He decides to do a tension connection. And these are 20-ton concrete beams. Now they're reinforced concrete. But rather than sticking it on top so it's in compression, the joint's in compression, he decides to make a tension joint. Stupid, 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 okay? Swiss architect, anyway. And then they were going to have plantings on here, and you were going to have a hanging garden. You were going to be like in the jungle or something. I don't know. I'm told it's a very nice building. I haven't been there since about this time last year. And anyway, so in August of 2012, they actually hung the first couple of beams, and they were using a martensitic stainless steel. Because you need some corrosion resistance, and they were using a 410 stainless. And it was martensitic. They wanted high strength. These are 20-ton beams. They're held by 2 3/4-inch threaded rods. You're going to hold 20 tons with 2 3/4-inch rods? Stupid, stupid, stupid. Anyway, well, not only that, they were supposed to tack weld the threaded rod up above here where it came through, and they hung these things up there, and one night a couple of them fell down. Now it was nighttime, no construction workers got hurt, they just dropped a couple of 20-ton beams on the veranda, okay? And afterwards they looked, and well, they had put these little tack welds to keep the rods from unthreading. Oh, stupid, stupid, stupid. And the engineer for the architect says to the contractor, says, why did you weld them? He says, have you looked at your drawing? And on the drawing, there's a weld detail. Weld it. So that was why the contractor welded it. Okay? It turns out the prior February, the people who were designing the concrete beams, who are concrete specialists, and they're not metallurgists, they'd sent a little note to the engineer saying, we don't think this is the right stainless, but we're not stainless steel experts. And you should ask the owner if this is the stainless steel he really wants to use. And the engineer sent back a note, says, we know all about this steel, don't bother us, okay? And so they didn't bother him, and they hung it in August, and the thing came down a couple of days later. A couple of days later after the welding, delayed cracking, okay, sort of rings a bell, right? High hardness, martensitic stainless, okay? So they repaired some of those things, and they decided to put nuts on or something, I don't remember, get rid of some of the welding. So in November, they hang some more, and they come down, okay, about 4 weeks later. And so this was December of 2012, okay. Everybody's all up in arms, and they decided, someone decided they shouldn't have used martensitic stainless steel. So they decided, okay, we're going to use 316 stainless steel because it has very good chloride corrosion resistance. And anyway, now they're starting to, they order like $7 million worth of steel to do this, and they're going to get behind on their contract and everything. And they're starting to fight over whose fault it was, who picked the 410 stainless, who welded it, why did these other things come down during construction. So eventually, the local general contractor calls me up and he says, can we meet with you tomorrow? I said, no. I said, I can meet with you Friday. So Friday morning, at 7 a.m., they're in my office, And they're explaining to me how this whole story I just told you, okay? And I said, well, I think they'd sent me some documents in between that I'd looked at, and I'd read them, and I sent the guy back an email. I said, stupid, stupid, stupid. No one should have ever used martensitic stainless steel here. I mean, basic, fundamental mistake. No one should have. A tension connection, you know, 100, these were supposed to be like 120 KSI or 140 KSI steel. I mean, just dumb. And then welding it in the field. So they had hired me. They wanted to fight over who was responsible for choosing this martensitic stainless. And I said, well, so are they building the building? I said, yeah, they switched to 316. I said, how long's your warranty? He says, a year. I said, well, 316 probably lasts a year. I mean, this building's supposed to last for 50 years, right? He says, what about 10 years? I said, well, I don't know if 316 will last 10 years. And he says, I said, what's 10 years? He says, statute of repose, which means if it lasts 10 years, you can't sue the original builder after 10 years, okay? I said, well, I don't know. You may not make 10 years with 316. So, and this is actually how the conversation went. So a couple of weeks later, I have to fly to Miami to meet with the owner, the architect, the contractor, big meeting, 40 people there, and I get up and I say, as a professional engineer, I could not sign off on this design. And I'm talking about the 316 now, which they just ordered $7 million worth of 316 to finish building the building, and they're starting to hang it. And the engineer who's responsible for having selected this material is defending it, okay? Oh, there's nothing wrong with this. You don't know anything about metallurgy. Oh, thank you, sir, okay. I think I do know something about metallurgy. But anyway, so they hired a firm, a civil engineering firm out here in Waltham that I used to be their metallurgist for about 30 years. And so they were actually coming in to advise people. Only those people actually knew me well enough, and they weren't going to go against me because I'd been telling them what to do for 30 years. Anyway, we have this meeting, and the owner's just sitting there. Who's going to pay for this $10 million problem on my $70 million building? But he's sort of aligned with the architect and the engineer because he's closer to them. And the contractor saying, look, if you don't figure this out, we're not going to keep on building your building. We'll finish the insides of your building, but we're not going to hang anything else out here because if it comes down and hurts somebody, we're going to be responsible. And so the general contractor, now the guy who owns the general contractor flies around his own private jet, but he's fairly well to do. But he said, we're going to do the right thing here. I mean, if Professor Eager says this, you know, this is going to fail, we're not going to hang any more steel. Which, when he says that, they could turn around and sue him for the whole delay of the project, okay, which is going to be tens of millions of dollars. So all these people are positioning themselves, and I'm sitting there saying, well, what's going on here? But I can remember the Hyatt Regency collapse. Anybody know the Hyatt Regency collapse in Kansas City back around 1980?
Similar to that.
Yeah. They had walkways. I mean, it was an indoor atrium, and they had tension threaded rods. They weren't stainless steel. They actually had a shear connection. The designer had designed it as a straight through connection, which may have been strong enough, but you couldn't run a threaded rod for 60 feet, so the erection detail, the guy had offset, you know, had one threaded rod with a nut and another one with a nut on the top, and it was a shear connection, and all of a sudden that shear connection couldn't take the load, and the big party, a couple hundred people died. Okay, came crashing down 4 or 5 stories in the inside. So I'm sitting there thinking, I said, well, you know, this is sort of like the Hyatt Regency, because you have people, now here you got people sipping the Chardonnay down here rather than up on the walkway, so they wouldn't fall, they just get crushed, okay, in the Hyatt Regency. But still a tension connection. Stupid, stupid, stupid. Why do you make tension connections? So I had the same sort of ethical dilemma. What am I going to do? So I called up the attorney the next day when I got back. I said, or maybe we said it as the way to the airport. I said, you know, I got a problem. If those guys are going to keep building this thing out of 316, I got to notify. I have a public responsibility as a PE, as a professional engineer. I can't let them continue to do that without warning somebody. I can't stop them from doing it, but I got to tell them that they have a serious problem. And he says, well, just write me a letter. So the next morning I get back to my office and I write the letter, and by 10 o'clock he's got a copy of the letter. He says, oh, don't write it to me. he says, write it to the general contractor, so rather than to the attorney. And I thought they were going to take this and read it to the other people. No, they mail it to the owners, which means they're now on notice. Okay, and they really have to show that to the City of Miami building authorities. Okay, who can shut the project down. Okay, because they've been notified. Anyway, it was I wrote a fairly firm letter that this was a poor choice of material. In the meantime, the engineer goes back and he kind of talks to his metallurgist in Sweden. They were using a Swedish steel company. They also asked me, what material could you use? I said, well, you could use, there's some nickel-based alloys you could use that have very good corrosion resistance in seawater. I said, you might be able to use a duplex stainless, but I'd have to look it up and research it, see if it'll be good enough at these stress levels in this environment. I said, I don't know off the top of my head. That's when I found out. Before, I thought there were just a few of these. I didn't know there was $7 million worth of metal here. All of a sudden, when they told me it was $7 million worth of metal. Anyway, the first response from the engineer was, well, we're 50 yards from Biscayne Bay and we're up 6 stories in the air, so it's not a marine environment. Pretty good, huh? I thought that's cute. I said, did you ever hear of hurricanes? They kind of come through Miami every now and then, and they have a salt spray that comes with them that'll get up 6 stories in the air. Okay. I said, I think that's a marine environment, okay, because I'd given them some references of how 316 is in tension can cause stress corrosion cracking, particularly if it's been welded. So anyway, it goes on for about 2 or 3 months, and eventually the engineers out in Waltham, we were sort of on opposite sides, but we were sort of trying to work together. And I'm sitting there, I'm not going to design this building for them. I didn't design the stupid tension connection to begin with, and I would have changed it to a compression connection where I don't have tensile stresses to cause cracks. And I'm not going to start telling them how to solve their problem. I can give them some, they got to make the decision. Otherwise, I'm the designer, right? And if anything happens, I got problems. And no one was paying me enough money to take on a $100 million liability. Okay, so, but these other engineers were working with the guys in Sweden, and the whole thing was sort of and they probably did $1 million worth of tests, and I'm just sitting there sending them papers saying this is a bad choice. So they finally did go to a duplex stainless steel. And they finally got some of the duplex in a big rush. And I think by June or July they were putting up duplex stainless steel, and they had their opening in May. But they're still going to have a fight over who chose the martensitic stainless, and the engineer is still trying to defend their choice that there was nothing wrong with martensitic stainless. Well, I wouldn't accept that from a first-term sophomore. Okay, and now that I put it on, it'll go onto YouTube. And they can probably play this for me at the trial, and I don't really care because those are idiots, pure idiots. Now, I couldn't say that at trial, but if they want to play that part of this video at trial, it's okay with me, okay? See, I can't get up and call them idiots live, but when I'm talking to my students, okay, of how stupid this mistake was, okay, you know, and this is one of the world's larger engineering firms. They got hundreds of engineers all around the world. And the problem, well, anyway, it's when you're trying to use a sophisticated material, stainless steel in a marine environment, susceptible to corrosion cracking, and you got problems. Anyway. So that's that. We got a little bit more time. Let's go to ferritic stainless steels. The problem with ferritic stainless steels, and some of the medical instruments are actually ferritic stainlesses, like a 430, and they don't turn to martensite because of the ratio of carbon and nickel and chrome and stuff. The problem with the ferritic stainless steels is the same thing as we had with the Liberty ships, which were not stainless steels, obviously, but carbon steels or ferritic steels have something called a ductile brittle transition temperature. And so it's impact energy versus temperature. And remember, I told you the Liberty ships, we learned it's not just the force of fracture, it's the energy of fracture. And this is what Polini and Morris Cohen at Polini at Naval Research Lab and Morris Cohen and others, people had known about this for years, but they didn't really learn how to design with it until the 1950s. And the steel will change its resistance to fracture. It'll be brittle fracture down here, less than, this is in joules, so 20 joules is 15 foot-pounds. So typically the Coast Guard uses like 30 joules, okay, or 20 foot-pounds. The U.S. Navy often uses the same thing, okay. So this is in joules rather than foot-pounds, but it's about the same. This is brittle, very brittle down here, barely acceptable here, and a good piece of steel is up here at 50 or 80. And so this is an as-received steel. This is a shielded metal arc weld, and you can see we shifted the ductile brittle transition temperature from around 30 or 40 degrees. The midpoint here is often called there's lots of different areas on this curve that people pick, but let's say this was good for 40 degrees Fahrenheit, or this is 40 degrees centigrade, okay, for these ferritic stainlesses. If you weld it, you increase the temperature to well above room temperature or anything you're going to use. And if you do gas metal arc welding with a higher heat input, it makes it even worse. If you do a simulated heat affected zone, you get grain growth basically from the welding, and you can destroy your toughness in these things if you weld them. So that's one of the problems with ferritic stainlesses. We do sometimes weld ferritic stainless, but usually only if it's sheet material. Sheet material, you don't have to worry so much about brittle fracture. Okay, we have a different type of stress state called plane stress rather than plane strain. And so I'm not going to talk a lot about ferritic stainlesses because you're not going to use them in heavy sections, or even anything above 1/8 of an inch is a heavy section for ferritic stainless. And they are used, but you have to be really careful about how you use them. The problem with austenitic stainless steels, things like the 316, is you can have, if it's straight 316 and it has not been welded, you can make a weld, and in the heat affected zone there's a particular temperature range between, let's say, 600 and 1000 degrees Fahrenheit in the heat affected zone, where you can precipitate chromium carbides if you have more than 300 parts per million chromium or carbon in your steel. And what happens is, here's your grain boundaries. You actually precipitate chromium carbides. The carbon can diffuse from large distances because it's a nice light, small element. The chromium can only diffuse from a few, maybe 10 microns away during the time you have. And so you get a chromium depleted region right in here, and chromium carbides. Nothing wrong with the chromium carbides, okay? The problem is the chromium depleted region. Another view of it looks like this. If you plot it, here's your carbide, which is very high in chromium, greater than 70% chromium. This is chromium versus distance across a grain boundary. So you have this little chromium carbide, very high in chromium, but the carbon is diffused from far away. The chromium is only diffused from a short distance away, and you end up with a chromium depleted region. And you do get down to 6 or 8% chromium in that depleted region, which is less than the 12% that usually gives you your stainlessness. I now have a region at the grain boundary that's depleted in chromium, and this becomes anodic compared to this as the cathode. I have a huge area, and I just stress corrosion crack right through this. If I use the right type of etchant, which is a 10% oxalic acid etch, there's an ASTM procedure A262. It has a bunch of different procedures for testing for what we call sensitization. This is called sensitization. You can take this steel, it'll be fine as it comes from the steel mill, everything cooled down at a uniform rate. You weld it, and now at the grain boundaries, the chromium has formed carbides if you have a little bit of carbon in your steel, and you run into a very sensitive, easily etched grain boundaries. This picture actually came out of the ASTM. They didn't reference it, but they stole it from the ASTM specification. So what we what General Electric and other people did, because they didn't think they would run into this problem. But if we go back to this category of stainless steels, they basically went from 304 stainless to 304L. And in fact, they got the carbon down to less than 100 parts per million. 304 stainless has a specification the carbon can be between 300 and 800 parts per million to be in spec. That will cause chromium carbide precipitation during welding. If you go to 304L, which we've known about since the 1940s, but until about 1960 it was very expensive to produce. You had to melt your stainless, take off the slag, put another slag on to try to draw the carbon out. And I think I mentioned this. There was a guy who did his doctoral thesis in the late 50s here, in the basement of Building 8, who found a way to bubble argon through the bath of the molten stainless and remove the carbon to very low levels. It used to like double the cost of stainless steel back in the 1940s to go from 304 to 304L. Well, all of a sudden, it costs almost nothing to go through this process, which is called argon-oxygen decarburization. So you take the carbon out of the stainless steel, you don't have to do a double slag practice, and almost all of the stainless steel today, 304, is 304L. Certainly anything other than sheet material. Some of the sheet material is still straight 304. Some of the rod that's never going to be welded is 304, but most of it is 304L. What General Electric did for their reactors, they actually went to an ultra-low carbon and a specification. It had to be less than 100 parts per million. But then they found the carbon was adding strength, and they found their stainless steel didn't have enough strength when they got below 100 parts per million carbon. So now General Electric uses LN steel, where they go to very low carbon and they add some nitrogen back to replace the carbon to bring the strength back up for the stainless steel. And that's an extremely easily welded steel in terms of carbide precipitation and stress corrosion cracking. So they got around a lot of the stress corrosion cracking problems that way. Here is actually the time scale for stress corrosion cracking as a function. I said 600 to, I think I said F. So it's between 600 and 900 degrees centigrade. This is the regular old 304, 0.08 carbon max. This is the bottom range for the 304. So 304 is in here. Within less than a second, you can form these chromium carbide precipitates that will lower your chrome at the grain boundaries and cause stress corrosion cracking. We get intergranular cracking at the grain boundaries, which looks sort of like hydrogen cracking in steels, but remember I told you stress corrosion cracking occurs at the anode and hydrogen cracking occurs at the cathode. If I go to less than 0.03, which is the 304, then I can change this to many minutes. Well, certainly my welding is going to be here, and the cooling of even a big heavy plate is going to be in 1 to 10 or 20 minutes or 30 minutes, depending on what I'm welding and whatnot. So if I get to very low carbon, I essentially, like less than 100 parts per million, I can get rid of the chromium carbide precipitation. I'll show you some of the types of, a little bit scary, of what a cracked material might look like. So this actually is caustic cracking, but it's transgranular stress corrosion cracking, but that's quite a bit of cracking in that 308L weld metal carbon. Well, this is carbon steel shell with 308 weld metal, but 316L tube sheet in some heat exchanger. And they had some caustic sodium hydroxide solution that these things just crack. And that's basically what happened to my stuff that just, my hot dog cooker. It was basically stress corrosion cracking, although that was in the base material. Just to show you one last thing on chloride cracking in stainless steels before we take our break. So if you look at nickel content versus time to failure in hours, and this shaded region is you'll see it's the shaded region represents nickel range of many austenitic stainless steels. So we tend to use austenitic stainless steels in this range, in the shaded range, which means that you could get, if you test in boiling magnesium chloride, which is a standard ASTM test for looking at chloride cracking resistance of stainless steels, we have things that'll fail within an hour. Okay? So it is a chemical reaction. It's not necessarily hydrogen exactly, but it's similar to you're eating things away. If you have much higher nickel, like the Inconels, with 60%, you won't have this type of problem at all, and that's one of the reasons for going to the Inconels. You have no problems, generally don't have problems with chlorides. Or if you go to the Ferritics, but the problem with Ferritics and martensitics is the martensitics will hydrogen crack, and the Ferritics with grain growth and impact toughness problems, but you can go to some of the Ferritics when you want chloride cracking resistance. At one time, actually, anybody ever have a very low temperature boiler in their home that actually exhausts wet steam out the side of the house rather than hot steam going up the stack? No one's got a high efficiency boiler? You do? Okay. I've got one too. Yep, and they exhaust out the side and you see steam coming out, right? Right out the side, you know, for me it's 5 yards from my front stoop, and when the boiler goes on, you see this steam coming out behind my rhododendrons. Okay? Because that's where it exits. I had a fireplace and I said, well, can't you send it up the stack? And they said, only if we line the stack with super ferritic stainless steel. Actually, they didn't say that. They told me, only if we line it with this special stainless steel. And I said, what type of, and I think I did ask, or I looked it up and found out what type of stainless steel, which was one of the super ferritics. And it turns out, when you're burning gas or oil or whatever, they're worried about if you send all that carbon monoxide and there might be some chlorine or whatever if you're an oil burner, and I'm burning gas, but there shouldn't be any chlorine in my gas, but some people are burning oil and there'll be some chlorides in your oil, and they don't want cracks on your liner for your chimney. They want a super ferritic that can take moist chlorides and not crack, okay? And they were going to charge me, this was in my poorer days, they were going to charge me like $2,000 or $3,000 to line my stack. This was back in the 1970s. That, you know, I could have paid my mortgage for 6 months for whatever they wanted. So I didn't do it, and so I just blew the steam out the side, which I'm still doing all these years later. But the super ferritics can take moist hot chlorides and not crack. Austenitics, they'll be gone in an hour, okay, and something like that. So there are regulations, and I still steam heat my rhododendrons during the winter, okay, or whenever we're using a lot of hot water, because my boiler runs my hot water. Okay, let's take a break for 7 minutes, and then we'll let the two people